Hello again, physics friends. Today we're talking about the so-called delayed choice experiment. As a refresher, we've seen already that a beam splitter with two detectors can be used to show that single photons exist because through anti-coincidence, meaning that if you have a source of single photons, either one detector or the other one fires, but not both. Okay. But then we also saw that if you add a second beam splitter, so now we have two beam splitters and you form an interferometer, now you see interference effects at these detectors, X and Y. And in order to have interference effects, you cannot allow a photon to take one path or the other. Okay, so for the anti-coincidence experiment, detector DR clicks because the photon reflected and took that path, or detector DT clicks because the photon was transmitted through the beam splitter and triggers that detector. In the interferometer, the number of clicks in each detector follows a very specific pattern that's related to the relative path lengths through this interferometer for path X and path Y. And that interference pattern would not exist if a photon took one path or the other. But now we're forced into a very curious situation because in order to take one path or the other, the photon has to either reflect or transmit, and that happens at this first beam splitter. But how does the photon know, in this case, to act like a particle and reflect or transmit? Well, in this case, to act like a quanton and to not take one path or the other. It seems like the presence of this second beam splitter is really important, but that second beam splitter comes after the first. Okay, so what we're trying to do is get a sense for how the photon knows to behave like a particle or like a wave, and we're going to explore something called the delayed choice experiment, in which the second beam splitter is either injected or inserted or not. And if it's inserted, it becomes this experiment, and if it's omitted, it's this experiment. And we want to see what happens in that case. So here's our apparatus. We have our input from a single photon source, beam splitter 1, 2 paths, mirror, mirror, and then beam splitter 2. But beam splitter 2 can be injected or inserted rather into the system or removed from the system. And it can be done very quickly, and that choice is made after the photon has passed beam splitter 1. Incidentally, this idea of delayed choice, meaning choosing to put in or not beam splitter 2 after the photon has passed beam splitter 1, was proposed by a physicist named John Wheeler in the late 70s and was actually implemented and done experimentally by Helmuth et al. In 1987. The key idea, just to summarize, is that if Wheeler's delayed choice experiment is capable of detecting either particles through the anti-coincidence behavior or waves via the interference behavior, but the experiment is designed so that choice of which aspect to observe is delayed until after the photon has passed beam splitter 1, which is, loosely speaking, after the photon decides what it's going to be, because the photon makes that decision at beam splitter 1. So if you imagine in this apparatus, right, if beam splitter 2 is in, then this is exactly the same Mach-Zehnder interferometer that was used for single photon interference. If you remove beam splitter 2, then a single photon can only get to detector Y if it traveled on path Y. So it comes in, reflects, and then makes it to detector Y. Remember, beam splitter 2 is not in for this scenario. In that case, in order to get to detector X, a photon must transmit at beam splitter 1, reflect off the mirror, and make it to detector X. So without beam splitter 2, we have which way path information, because if detector X clicks, then we know the photon took path X, and if detector Y clicks, then we know the photon took path Y. So let's think about this for a minute. Let's say that a photon that comes to beam splitter 1 has to make a decision. Is it going to reflect or transmit and take one path or the other? or is it going to somehow exist in a superposition of taking both paths? Well, the claim, apparently, based on the previous experiments, if beam splitter 2 is out, then the photon either reflects or transmits, but not both, and not neither. And if beam splitter 2 is in, then you have the interferometer, and the photon does not take one path or the other, but it takes a superposition of both paths. Okay, so let's assume that this photon has to decide what to do based on the experimental configuration at the instant that it reaches beam splitter 1. In that case, let's say beam splitter 2 is out, okay? In that case, the photon comes, it now only has one beam splitter because beam splitter 2 has been removed, and it has to act like a particle, so it will either transmit or reflect. But then as it's traveling, beam splitter 2 is now reinserted into the system. Well, if that's true, then we're gonna not be able to have interference, right? Because if only one path was taken, there's no opportunity for interference, even though beam splitter 2 has been put back in. The problem, though, is that when you do the experiment, if you start the experiment with beam splitter 2 out, and midway through the experiment when the photon has passed beam splitter 1, you put beam splitter 2 back in, you do see interference. Okay? So this idea that the photon somehow has to make a decision of what to do at beam splitter 1 based on the configuration of the experiment at the instant when it's at beam splitter 1, that can't be true. That can't be true because beam splitter 2's presence later in the game, even after the photon has passed beam splitter 1, will determine whether or not there's interference. Indeed, the experiment by Helmuth et al. In 1987 found that no matter when beam splitter 2 was inserted, there was an interference pattern measured. And conversely, if the experiment was started with beam splitter 2 in place, and then it was subsequently removed, then no matter when it was removed, interference was not observed. And this is exactly what quantum predicts, right? If there's no opportunity to know which way path, then you will have interference. But if which way path is known, then the photons behave like particles. Somehow, the photon, in quotes, knows whether or not beam splitter 2 is eventually going to be present. And we either get or don't get an interference pattern accordingly. So this to me is fascinating and bizarre. But you can make it even more dramatic by taking this delayed choice experiment to an extreme. And this extreme extension, was also proposed by John Wheeler. The proposed experiment looks something like this. We have quasars in the very distant universe, but they're so-called double quasars, and they actually are the same source, but their light is reaching us from two different paths. So it appears to be two different objects in the sky. So we know from general relativity that mass, like a galaxy or clusters of galaxies, can bend the trajectories that light take, and you can form what are called gravitational lenses. So light from a very distant quasar, normally in the absence of this galaxy, would come straight to us. But in the presence of this galaxy, light that would have been emitted up this way is now bent down to reach the Earth. And from the Earth's point of view, it looks like that light is coming from a location like over here. But light also can take a different path like this and arrive at the Earth, and that light appears to be coming from over here. So from the Earth's point of view, it looks as if there are two sources, two quasars, even though really there's just one. Okay. Well, this looks a whole lot like an interferometer. You have a source and two paths that recombine. Okay. Now, in order to really make it an interferometer, we would need a beam splitter to recombine the paths here at the Earth. Okay. If you don't have the beam splitter, you would just see two quasars. That would be like the anti-coincidence experiment. Either the light from the quasar took one path or it took the other. Okay. But if you put a beam splitter here to recombine these beams, then you would see an interference pattern, much like you do in the single photon interference experiment. But here's the crazy thing. These quasars are billions of light years away from us, and the light has been on its journey from the quasar to us for billions of light years. And yet we can delay the choice of whether or not to put in a beam splitter right up until the last moment. And the claim is that if we don't put a beam splitter, then the photons behave as particles, and they took one path or the other. And if we do put in the beam splitter, then they behave like waves, and we get this interference pattern. But this also doesn't make any sense, because how could our choice today have any impact on the billion-year history of light travel from the quasar to us? It seems like our action in this present moment has consequences that stretch way back into the cosmic past. If nothing else, this delayed choice experiment really shows how problematic the simple wave-particle duality description is, right? Once light is in an interferometer, we just can't think of it as either a wave or a particle. And we can't kind of mash together these two hybrid descriptions to like wave-particle duality. All of these descriptions are inadequate, and we basically need, instead of a composite picture of light that's stitched together out of classical ideas, we really need a new concept, right? A new point of view that's fundamentally quantum and different from the world of classical physics. So we really need to think of a photon as a quanton, not as something that's wave-like and particle-like. It's just simply a quanton. Now, importantly, there's nothing in the delayed choice experiment that is in violation of quantum mechanics. So you can do a calculation using quantum mechanics to make a prediction for what you'd see in this beam splitter in-or-out experiment, and your prediction made with quantum mechanics agrees wholeheartedly with experiment. Okay. And yet, this experiment is still unsettling, because it's hard to interpret the meaning of these experiments, mostly because we just insist, often implicitly insist on ascribing the photon as choosing one path or the other, even though that's a very classical idea. So a lot of the challenges we face when thinking about and interpreting these experiments comes not from a disagreement with quantum, but rather a difficulty for our ability to understand, quote unquote, what the photon is doing. So quantum is very happy to provide us with the correct probabilities for various detection eventualities, and those are in agreement with experiment. But the nature of quantum and the interpretation of the experiment leaves much to be desired at this point. Okay, well, I hope you've enjoyed our discussion of the delayed choice experiment. Until next time, be safe and be well.